Hey guys, this is Miss Holtz, and we've talked a lot about what a projectile is and also two-dimensional vectors. So now we're going to apply two-dimensional vectors to projectile motion. And those vectors include velocity and acceleration. So we've already talked about force vectors on a projectile and how at each point in this projectile's motion, it's only experiencing the force of gravity downward. So we also know that forces cause acceleration. So this gives us a lot of information about the acceleration of a projectile. So at each point during the projectile's motion, it's experiencing an acceleration downwards at every point. And the value of that downward acceleration is little g, the acceleration due to gravity, which is negative 9.8 meters per second squared. And we also know that this is negative because it's pointing downwards. So let's think about Newton's second law with this scenario. The sum of the forces equals mass times acceleration. And in this scenario, our only force is the force of gravity, which is the same thing as weight. You probably know this equation better as in terms of weight. But the force of gravity, or weight, is equal to m times little g. Suppose they should have vector symbols on top too, shouldn't they? So when we're talking about a projectile and it only has the force of gravity acting on it, it only has an acceleration due to gravity. So that's why all of these acceleration vectors have the magnitude of little g, which is negative 9.8. Now that we know something about its acceleration, we can determine more information about the velocity of a projectile. So since the acceleration describes a change in velocity, the downward acceleration causes a change in the y component of the velocity. And let's take a look at what that would look like. So the velocity at all points in the motion of this projectile is changing. So the length of the arrow in the y direction is getting smaller and smaller as it goes towards the top of its motion. And this makes sense because if you were to throw a ball straight up into the air, it gets slower and slower until it reaches the top of its motion, at which point it has a zero y component of its velocity. And then as it goes down, it gets faster and faster and faster. So each of the magnitudes of the velocity y component arrows gets larger and larger as you start going down. So the y component of the velocity is always changing during a projectile's motion. Now let's think about the x component. Since there is no horizontal acceleration, remember acceleration was only little g pointing downwards. So since there is no horizontal acceleration, there is no change in the x component of the velocity. So this projectile here was thrown at an angle, and so its velocity in the x direction is always going to be the same length because it's not changing at all. So even at the top, when it stops in the y direction, it's still traveling in the x direction at the same velocity. So if we think about this in terms of algebraically, we could say that the velocity in the x direction initially is the same as the velocity in the x direction finally, or at any point in its motion, really. Okay, so we have information about force vectors, acceleration vectors, and these components of velocity, but what about the composite velocity for each of these points in time? We can do that by adding the two components together. So to add these components, I'm going to move this x arrow, this x component arrow, and I'm going to put the tail of that arrow to the head of this first vector I'm adding to it. And when I add those together, my resultant vector is going to go from the tail of the first arrow to the head of the last arrow. And that would be our velocity, our complete velocity for that point in time, which happens to be our initial velocity in this scenario. And this vector makes sense because our projectile is moving up and to the right in this general direction. So the velocity arrow tells us about which way it's going. Now let's do one more. We have our x component, and I'm going to move it up here so that we can draw our resultant vector. And when I draw that one in, it's pointing in a little bit different direction than the first one. And it's also pointing in the direction that it's going at that point in time. So from what we know about two-dimensional vectors and projectiles, we can determine information about the force acting on a projectile, the force of gravity. We can tell about the acceleration acting on a projectile, which is little g, acceleration due to gravity, and we can also tell information about the components of the velocity and the total velocity of a projectile.